Hello, my junior sis. Welcome to another biochemistry lecture series. It is your great science tutor Lorenzo, and we'll be dissecting what we call beta oxidation in this video. So, if you are new to my channel, make sure to subscribe and turn on your post notification button so that when I drop any video, you'll be sure to be notified. Like I always say, if you need any video to be made for you, make sure to write it down in the comment section. When I go to it, I'll make that video for you. So, let us jump right into the video. So talking about beta-oxidation, because we said that the fatty acid released during lipolysis is transported with albumin to the liver, especially the mitochondria, to undergo what beta-oxidation. So those fatty acids are converted to form of acetic CoA. So acetic CoA is an intermediate of TCA, which enters the electron transport chain to form what ATP. So the conversion of fatty acid to ATP is what we call beta oxidation. So it is forming in the mitochondria of the liver, but very long chain fatty acid and branching fatty acid are converted in the peroxisome. So in the peroxisome, they have specific enzyme there that break down very long chain fatty acid and branching fatty acid. So now we will talk about what are the factors that stimulate or inhibit. So very simple, the same way you know it. The presence of glucagon, fast instantaneous exercise, and the high level of cortisol stimulate what beta oxidation, glucagon production. So when the glucagon level is high, glucagon favors beta oxidation by favoring what lipolysis, and a decrease in insulin also favors lipolysis. So when you have increase in insulin, it favors what lipogenesis, which inhibits what beta oxidation. Also a well-fed state, when there's increase in lipid in the body, you do not need beta oxidation. So simple. Beta oxidation process undergoes three basic stages. So we have the activation of the fatty acid, which we transported using albumin. We will not transfer it from the cytosol into the mitochondria, and the beta oxidation process proper. So now in the first one, which is the activation step of fatty acids, first of all, fatty acid is converted to fatty acid CoA by fatty acid synthetase. Again, fatty acid is converted to fatty acid CoA by fatty acid synthetase, or a thiokinase, utilizing ATP. So ATP will be converted to ADP in this reaction. So now from fatty acid to fatty acid CoA in the cytosol, what is the next thing you do? Then you now transport this fatty acid CoA. Now you should also know that the fatty acid CoA can't be transported just like that into the inner mitochondrial matrix. So you need a carrier protein. So the carrier protein here is carnitine. So carnitine has three basic enzymes. We have carnitine acid transferase, which if you are using palmitic acid, you say carnitine palmital transferase. So in some textbook you see palmitic acid is used, which is carbon 16 fatty acid. So it's still the same thing, carnitine acid transferase or carnitine palmital transferase. So we have cat1, which is outside, it's present in the outer part of the mitochondrial matrix. So you have the carnitine transferase, which is present in the middle part of the mitochondrial matrix, while the inside have cat2, which is carnitine acid transferase, or CPT, which is carnitine palmital transferase type 2. So what do they do? Simply, so what do they do? First of all, the fatty acid CoA can be transported. So what will happen? It binds to cat1. So the cat1 takes away the CoA group from it to form fatty acid carnitine. So when fatty acid CoA combine with carnitine, it form fatty acid carnitine. So the carnitine acid transfer, it holds up, it takes the CoA to hold it and transport fatty acid carnitine into the reaction, into the inner mitochondrial matrix. So it gives it to carnitine translocase. So carnitine translocase transports the fatty acid carnitine to the inner mitochondrial matrix. So it hands it over to cat2. So cat2, which is carnitine acid transferase type 2. So what happens? So the carnitine acid transferase now takes the carnitine, send it back to the outer mitochondrial matrix, and give it back the CoA. So if it gives it back to CoA, now it will form fatty acid CoA. So when the carnitine is sent back to the outer mitochondrial matrix and the CoA is given back to the fatty acid, so what will it form? It will form fatty acid CoA for the beta oxidation proper. So very simple. So in the beta oxidation proper, we have some reaction. So the first reaction we have is oxidation, hydration, oxidation, thiolate cleavage. So when you remember the mnemonic O hot, oxidation, hydration, oxidation, thiolate cleavage. So you remember the beta oxidation that occurs in the inner mitochondrial matrix. So the first one is oxidation. When you utilize the enzyme acyl CoA dehydrogenase enzyme, which catalyzes the conversion of fatty acid CoA to trans-zeta 2 Enoyl CoA between carbon the double bond between carbon 2 to carbon 3. So when you convert fatty acid CoA to trans-zeta 2 acyl CoA using acyl CoA dehydrogenase. So when you use this enzyme, now what are you using? You are converting, you are what, reducing FAD plus to what, FADH2. So when you reduce FAD plus to FADH2, what you are converting, what, fatty acid CoA to what, trans beta to what, acyl CoA. Now the acyl CoA dehydrogenase differs from long chain, medium chain, short chain fatty acid, so they are very, very different for everybody. So we are treating this one is what, long chain fatty acid. So now the next reaction here, the trans beta to acyl CoA between carbon 2 to carbon 3 is what, accept water, is hydrolyzed to form what, L beta what, hydroxy acyl what, CoA, using what, Enoyl CoA what, hydratase. So Enoyl CoA hydratase catalyze the conversion of what trans beta to acyl CoA between what, carbon 2 to carbon 3 to what, L beta what, hydroxy acyl CoA. Don't forget it. So the next one now, L beta hydroxy acyl CoA is what, is reduced or is oxidized to what, L beta keto acyl CoA. Don't forget, L beta hydroxy acyl CoA is what, oxidized to what, L beta keto acyl CoA, utilizing what, NAD plus to what, NADH. Don't forget it. So the first coenzyme we are using is FAD plus. So FAD plus in the first dehydrogenase enzyme in oxidation is converted to what, FADH2. While in this second one now, NAD plus is converted to NADH. When what, L beta keto L beta hydroxy acyl CoA is converted to L beta keto acyl CoA, using what, L beta what, hydroxy acyl CoA what, dehydrogenase. Don't forget it. Now the last one is Thiolytic cleavage. So in the Thiolytic cleavage, what happens? L beta keto acyl CoA utilizes what, beta keto thiolase. So they utilize beta keto thiolase and cleave to form what, 1 moles of acetyl CoA, and if we are using cysteine compound, usually palmitic acid, to form what, 14 carbon. So the 14 carbon will go to the next reaction and undergo O-hot again. So now when we have cysteine carbon, when we are using cysteine carbon fatty acid, what happens? At every cycle we are forming 1 moles of what, acetyl CoA. So when we form 1 moles of acetyl CoA, 14 carbon will go back, we form the second mole of acetyl CoA, 12 mole will go back. So it will occur for what, 7 cycles. So in 7 cycles you will form what, 8 acetyl CoA, and the reaction would have gone what, 7 times. So if you go 7 times, you're forming 8 acetyl CoA, and you'll be forming 7 FADH2 and 7 NADH2. So no need for the activation step, no need for the transport step. The only reaction, the cycle will continue to the continue in the inner mitochondrial matrix. So very simple. So don't forget that. I hope it all made sense and you understand the beta-oxidation process. Very, very easy. So we discussed the activation, we discussed the transfer, we discussed the beta-oxidation proper in the inner mitochondrial matrix using OHOT. So hope you understand all I've said and all the reaction. So if you are new to my channel, make sure to subscribe and turn on your post notification button so when I release any video, you'll be sure to be notified. So let us enter the energy profile.